Hello everyone, welcome back to the channel. If you've ever written a program that worked perfectly on your laptop but suddenly stopped working on another computer, then this video is for you. Today we're going to understand Docker from the very beginning. Let's imagine a simple situation. Suppose I'm a bioinformatics researcher. I developed an RNA-seq pipeline on my laptop. I installed Python. I installed R. I installed Bowtie 2, SAMtools, FastQC. Everything works perfectly. Now I send my project to my friend. He opens it on his computer. Suddenly, the program doesn't work. Why? Maybe his operating system is different. Maybe his Python version is different. Maybe some packages are missing. Maybe is another version. This problem is called dependency hell. Almost every programmer has said this sentence at least once. But it works on my machine. Docker was created to solve exactly this problem. So, what exactly is Docker? Docker is a platform that packages your application together with everything it needs. Instead of sending only your code, Docker also sends the operating environment, software, libraries, dependencies, and configurations. Everything is packed inside something called a container. Now imagine taking that container to another computer. Whether you run it on your laptop, a university server, the cloud, or an HPC cluster, the environment remains exactly the same. That's why Docker's philosophy is build once, run anywhere. Let me explain Docker with a simple analogy. Imagine you love drinking tea. You're going on a trip. Instead of depending on someone else's kitchen, you carry your own tea kit. Inside your bag you have tea leaves, milk, sugar, and a kettle. Now no matter where you travel, you can always make the same tea. Docker works exactly like that. Many confuse Docker with virtual machines. Although both provide isolated environments, they work differently. A virtual machine creates an entirely new computer. It has its own operating system, its own kernel, its own storage, and memory. That's why virtual machines are usually very large and take longer to start. Docker works differently. Docker shares the host operating system's kernel. Instead of creating another operating system, Docker only packages the application and its dependencies. This makes Docker much lighter, much faster, and much more efficient. A container can start in just a few seconds. Now let's understand 4 important Docker terms. Docker image. Think of an image as a blueprint. It contains all the instructions needed to create an environment. However, an image is not running. It is simply a template. Docker container. When we run an image, Docker creates a container. A container is simply a running instance of an image. An easy way to remember this is recipe equals image. Cooked food equals container. Dockerfile. A Dockerfile is simply a text file. Inside it, we write instructions such as start with Ubuntu, install Python, install FastQC, install copy my scripts. Docker reads these instructions and automatically builds an image. Docker Hub. Docker Hub is an online library. Think of GitHub, but instead of source code, it stores Docker images. Thousands of ready-made images are already available. Ubuntu, Python, R, MySQL, Jupyter, bioinformatics software. Everything is already prepared. Let's see why Docker is so useful in bioinformatics. Suppose I want to perform RNA-seq analysis. Normally, I would install FastQC, trim galore, SAMtools, feature counts, R, and DESEQ2. That can take hours. Instead, I simply download a Docker image that already contains all of these tools. Now I can run exactly the same pipeline on my laptop, on a university server, or on cloud computing. Even if my collaborator lives in another country, we both use the same software, the same versions, and obtain reproducible results. That's why Docker has become extremely popular in computational biology. Now let's summarize the Docker workflow. Everything starts with a Dockerfile. Docker reads the Dockerfile and builds an image. When we run that image, Docker creates a container. Inside the container, our application runs. Docker eliminates dependency conflicts. Installation becomes much easier. Research becomes reproducible. Collaborators can use exactly the same environment. Deployment becomes faster. Docker works on laptops, servers, cloud, and HPC systems. It also saves a tremendous amount of time. Today Docker is used almost everywhere. Bioinformatics, machine learning, artificial intelligence, web development, data science, cloud computing, DevOps, genomics, proteomics. If software needs to be portable, Docker is probably involved. Now let's install Docker on our system. First, open your web browser and go to the official Docker website. I am writing the official Docker desktop download link. Always download Docker from the official website. This ensures you get the latest and safest version. Now simply open this link in your browser. Once the website opens, click on Download Docker Desktop. Now that Docker is installed, let's learn the basic Docker commands that you'll use almost every day. Docker automatically detects your operating system. Once the installation is complete, restart your computer if prompted, and then launch Docker Desktop. We'll verify that Docker has been installed successfully and learn our first Docker commands. Now that Docker has been installed successfully, let's verify it by checking all the Docker images available on our system. The repository column shows the name of the image. For example, here we have images like Ubuntu, FastQC, and HISAT2 pipeline. The tag column represents the version of that image. If you don't specify a version while downloading, Docker usually uses the latest tag. Next is the image ID. To download an image, we use the docker pull command. Now let's try downloading the FastQC Docker image. As you can see, Docker returns an error. Failed to resolve reference, not found. Don't worry, this is a very common mistake, especially when you're working with biocontainers. Always verify the correct image name before running Docker pull. A small difference in the repository name can lead to a not found error, just like we saw here. Here, Biocontainers, FastQC is the image name, and version 0.11.9_CV8 is the tag, which identifies the exact version of the FastQC image. When I press enter, Docker checks whether this image is already available on my system. As you can see, Docker displays the message. Status: image is up to date. As you can see, FastQC returns its version successfully. Biocontainers is a community-maintained repository that provides containerized versions of thousands of bioinformatics tools. Now, let's search for an example. I'll search for HISAT2. As you can see, multiple results appear because Biocontainers hosts different packages and related tools. Biocontainers provides the exact Docker command needed to download the container. You'll also notice that Biocontainers provides commands for Conda, Docker, and Singularity. Depending on your workflow or computing environment, you can choose the package manager or container platform that best suits your needs. Now let's download the HISAT2 Docker image using the command we copied from the Biocontainers website. I'll simply paste the command into the terminal and press enter. Docker now connects to the registry, downloads the required image layers, and stores the image on my local system. Once the download is complete, Docker displays the message. Status: downloaded newer image, which confirms that the HISAT2 image has been downloaded successfully. So far we've learned how to find and download Docker images. Now it's time to create our first container and run HISAT2 directly from Docker. We've only downloaded Docker images using the docker pull command. To actually use the software inside an image, we use the docker run command. Here, I am running the FastQC image. This command is not being executed inside the Docker container. It is running on my local computer because FastQC is already installed on my system. We've only downloaded Docker images. Now it's time to actually use one. Instead of my Mac terminal, I am now inside the Ubuntu container. Now let's explore the container just like we would on a normal Linux system. You can see standard Linux directories such as bin, boot, dev, etc, home, lib, temp, usr, and var. These directories exist inside the Docker container, not on my local computer. Remember these two commands. Docker ps shows only running containers. Docker ps shows all containers. Now that we understand Docker basics, let's build our first custom Docker image. The goal is to create one Docker container that includes all the essential bioinformatics tools we'll need for RNA-seq analysis. In this example, we'll install FastQC for quality control, SAMtools for working with BAM and SAM files, HISAT2 for RNA-seq alignment, and Bowtie 2 for sequence alignment. Step 1. Create a project directory. Let's begin by creating a new folder for this project. This folder will contain a Dockerfile, which is the file Docker uses to build our custom image. I'll create a directory called bioinformatics_container and move into it. A Dockerfile is simply a list of instructions that tells Docker exactly how to build our image. We'll ask Docker to read the Dockerfile and build our custom image. This process may take a few minutes because Docker first downloads the base image and then installs all the required software. Let's create a container from our newly built image. The final step is to verify that all the software has been installed correctly. Congratulations, you've just learned the fundamentals of Docker and how it can simplify bioinformatics workflows. Thank you so much for watching. If you enjoyed this video and found it helpful, don't forget to hit the like button, subscribe to the channel, and press the bell icon so you never miss any future tutorials.